welcome back to a wonderful Tuesday rainy evening. So today, hello. All right, so today we will be talking about one of our most important abstractions in this course that we will be using over and over again, and that is processes. So we've already kind of laid the groundwork for them in the previous lecture. So what a process is it is an instance of a running program. Well, a program or application, right, I've been using those terms kind of interchangeably thus far, is just like a static definition. It's just that ELF file we saw before. So it just contains, you know, the instructions, any data that was associated, so like the string in that first example, any memory allocations it might use, symbols it uses. So like your actual programs you compile, right? If you use printf, somewhere in that executable, there'll be information in it that says, hey, I use printf. When the operating system loads me, you need to find printf in the standard C library, for example. Then your operating system would figure out how to actually do that. And then kind of what we care about in operating systems are things that actually run and execute. So a process is what executes a program. And what the kernel does is it manages processes. So a process is just an execution of a program, and then you can have many of them. And what a process is, it kind of encapsulates a bunch of different virtual resources. So you can think of it like encapsulating pretty much all the virtual hardware on your machine. So we already know and kind of discussed like a virtual CPU. So at the very least, the operating system, if we're virtualizing a CPU, it needs to keep track of registers for a process. And the most obvious register, if we care about program execution, is probably the program counter, right? But it also contains all the other resources the program would use when it is executing. So like memory and I/O, which we'll get into later. But for now, again, we'll just care about the CPU because we're all kind of used to that by now. So kind of just to very clearly separate it out, that every execution kind of runs the same code, right? If we have multiple processes of the same program, which you are allowed to do, right? Each of the executions will be running the same code, so there'll be the same block of code in every process, but where it is currently executing, which you can think of as the current program counter, would be different for every process, right? So execution is running a very specific part of it, and it can change between processes. So that's why you can run, you know, if you had a long-running program, right, and you were bored of waiting for output from it, you could just run another one if you wanted to, which would probably make the first one slower, but hey, you could do it. So why the operating system does it is just because it's more flexible. It's a good way to just encapsulate everything, especially when you're the operating system or kernel, and then you have to manage it, right? So it contains both the information for the program, so all the instructions loaded into memory, and anything specific to its execution. So again, where is it executing in the program? Where's the program counter? Maybe like what files does it have open? What libraries is it using? And things like that. So you can have multiple executions of the same program, and you can even, you know, allows a process to run multiple copies of itself, which we'll get into later when we learn how to actually create processes. So within a process, all that accounting information in operating system terms is something you'll find called a process control block, or PCB. And it basically just contains all the information specific to an execution of a program. So like process state, again, which would be, you know, also CPU registers. If you're the kernel and you have to keep track of who's running the CPU at any specific time, you probably have some accounting information for scheduling. So for instance, you might not want one program to run exclusively or run, you know, 100% of the time. So you probably need to track how long it's run for, so you know when to actually take the CPU away from it. But that'll all come in when we talk about actually scheduling and deciding what process to run at any one specific time. It also have memory management information. Again, that's a future lecture. I/O status, again, future lecture. and then any other type of accounting information that you might need to make decisions for. So process just encapsulates everything you need to know about a specific execution of a program. Okay, so since we haven't used threads, so if I say the words parallelism and concurrency, who thinks those mean the same thing? Oh, so everyone thinks they mean something different? Yes, hands up. No one has any hands? No one knows anything? All right, we got thumbs up for no one knows anything. So in plain English, if you're talking to a normal, sane person that doesn't study computer science or computer engineering, parallelism and concurrency mean the exact same thing, but because I guess we want to make life difficult for you, they actually represent two different concepts. So what concurrency is, it's basically being able to switch between two or more things. At the core of it, it means you can get interrupted. So the goal of concurrency is to make, progress on multiple things and be able to kind of juggle things around. While parallelism is doing two things at the exact same time. So they're completely independent. You don't have to juggle them. You don't do anything. You just run them both at the same time. And you want to kind of run as fast as possible. And that's kind of been the kind of trend lately. Right? We just keep putting more and more cores in our CPU and hope that more things can run in parallel and therefore things go faster. So kind of a real life situation. So let's say we are also polite adults since we're in university now. So you're sitting at a table for dinner, right? And you have, let's say you have 4 options. You can either eat something, you can either drink something, you can talk, or you can kind of gesture with your hands. But the kind of weird thing about this, so we can discuss everything, so you have to kind of bear with me on this, is that you're so hungry that if you start eating, you just won't stop, right? So you won't interrupt yourself for talking. You just will scarf down whatever's in front of you until you are done. So if we go off our definitions before, what tasks can be done concurrently and in parallel? So let's start with something easy. So can I talk and gesture in parallel? So hands up if I can do both those things in parallel, right? Because one with my hands, the other with my mouth, I can do them both at the exact same time and they make progress, at the exact same time. So I can do both of those. And I can also, right, talking's pretty much the same as drinking. I can both, so I can gesture and drink at the same time if I want to, but I'd have to just use one hand, but pretend that's fine. Okay, what about if I want to drink and talk at the same time? Can I do these in parallel? Okay, someone's very talented. Can I do these concurrently? Right? Yeah, I can do those concurrently because I could, take a drink, put it down, talk, right? I can interrupt myself. I can do whatever one of those I want at any specific time. I just have to switch between them. All right, well, what if I want to eat and drink at the same time? Can I do those in parallel? All right, another same talented guy. Okay, again, remember we're trying to be polite, polite, nice adults. So just one of us is, the rest of us are pretty polite. All right, so can we eat and drink concurrently? Oh, we got a few hands. Okay, so these are things we can't do concurrently because of that stupid rule I said where you're so hungry that you won't stop until you're done. So if I start eating, right, I can't start drinking because I'm so hungry that I wouldn't do it. Again, contrived example, but you might actually run into this when you're doing program execution. Let's see, what other example? Can I eat and gesture in parallel? Hands up for that. Yes, okay, we can do that in parallel. Can we do them concurrently? Hands up. No, right, I can't do it concurrently because it's that weird situation where if I start eating, I can't stop. So I could kind of interrupt myself from gesturing if I wanted to, but I'm either starting or stopping, and I'm either doing that at the same time as I'm eating or I'm not. I'm not interrupting myself eating to make progress for the other one. So hopefully these are all the combinations of these, right? So you can't eat and talk or drink because they're the same thing at the same time, and you can't you can't switch, so they're not parallel because they're using kind of the same resource, right? You're using your mouth for both of them. And they're not concurrent because of that stupid eating thing where you wouldn't be able to stop and switch. But you could eat and gesture at the same time, right? But you can't switch. Again, this is contrived most of the times where this might happen. So it's good to have an example of when that would apply, even though it's super contrived. So you could do those in parallel, but not concurrently, because you can't interrupt yourself to just make progress at one at a time. But you also can't drink and talk at the same time, but I could switch. So I can't do them in parallel because using the same mouth resource. But I could do them concurrently, which basically means I could switch and make progress on either one of those. Drink or talk and gesture at the same time because we can do them in parallel, different resources, and we could also interrupt ourselves because we don't have that stupid eating thing where we just won't stop. Right? So hopefully that makes sense about parallelism and concurrency, because I know in undergrad, for me, no one really explained it, even they were different, and if you look in the dictionary, it very much seems like they're the same thing. But so I'm introducing this so when we talk about actual threading and stuff, threading involves this stuff. So it's a good idea to get a base for it now, and we'll revisit it when we actually talk about threads. Okay, so this is kind of required reading for, if you go into the history of operating systems. So there was a programming model called Uniprogramming, which is like old batch operating systems. So has anyone ever used DOS? All right, we have like 2 people that use DOS. So DOS is an example of this. I guess now I get to officially feel old because I used DOS as a kid, and now no one else does. But in DOS, you can only run one program at a time, and it kind of sucked. So that's what the uniprogramming model is. You only have one process running at any particular time, so you don't have any concurrency. You can't do anything in parallel. You just have one thing running at a time, and if you want to run something else, well, you have to exit it yourself and then start up something new. Well, if you have multi-programming, which is kind of the operating systems now, what they're designed for, it allows multiple processes to run at the same time or concurrently. So they can run in parallel or concurrently, and it's up to the kernel to decide which is which. Right? In modern operating systems, you want to take advantage of all the hardware resources you can. So you want to run things in parallel as much as you can, and you also want to run them concurrently, so it looks like even more things are running at the same time. Even if you have only 4 physical CPU cores on your machine, you might be running 16 different applications at a time, and you want it to seem like you're actually running all of them at the same time, when even though, right, some of them have to be running concurrently if we only have 4 physical cores. So this is kind of the life cycle of a process. First, if you want to execute a program, you have to tell the operating system what you want to start executing and create a process for it, and then it will be in this created state where it's doing initialization, the operating system is loading it, so on and so forth. And then as soon as everything's loaded and everything's kind of initialized and it's ready to execute, it will go into this waiting state, which is also called, you could also call it ready if you want. It kind of depends who you talk to. And then it will kind of cycle back and forth for the majority of its life between this waiting and running state. So whenever the kernel decides to run it, it will be running for a period of time, and then it will, put it back to sleep. It'll take the CPU away from it, and it'll be back in this waiting state. And then sometimes when it's running, your program may request access to a file. It might try and be writing to disk or something like that, in which case it would get into this block state where it's waiting on some hardware resource and can't make any progress until that's completed. So then it will be in this block state, and then the operating system can go ahead and move it back to the waiting state whenever that I/O operation is complete, so then it can execute again. And then finally, at some point, you're going to call exit, and then it will transition from running to terminated, and it will be done. And yeah, there's a question?
So, like, when I use computers, like a process would be unresponsive, and then it has like a circle thing.
Yep.
Is it in the waiting state or is it in the block state?
So it's likely in the block state. if it's like the beach ball of death, it's probably waiting on some hardware resource or some network connection, or it could just be waiting on some resource or be in an infinite loop, in which case it would just kind of be running forever and not making any progress. And they have some smart things to know if it's not making any progress, even if you're running it. So it could either be running infinitely or in this block state. Yep.
If waiting, I assume you're waiting for like some CPU time.
Yep.
Blocked means you're waiting for hardware. Like, what's the difference between waiting for hardware resources and waiting for CPU time?
So if you're waiting for CPU time, you can execute at any given time. You're just waiting for the CPU. So the only difference between blocked and waiting, or waiting can also be called ready, is if the operating system decides to give you CPU, you can actually utilize it. So if there's free time and you're in the block state, you can't be running anyways, so it'll just skip over you.
And what would cause that? What would cause you to be in a block state?
So if you're waiting on some network resource or something, or if you're waiting on disk to write something back, right? If you're trying to read a whole file at once, it will just wait until because hard drives are really slow, right? So it'll wait for that. CPUs are way faster than hard drives. Yeah.
So it's kind of like for the thread scheduler, it's like waiting is like, okay, I can give you time.
Yeah.
And blocked is like, no, I can't give you time
Yeah.
until I get, like the hard drive comes back with something.
Yeah. Yeah. So the scheduler, when we ever get into that, is pretty much concerned with this loop here, right? Managing what's ready and what's running. And if it's blocked, it can't run on the CPU. Yep.
What's an instance where, like, why would the CPU wait for it to give some time? Like, I don't understand the point of waiting.
So waiting, right, if you look on your machine, you're going to have maybe hundreds of processes. So there's no way to run them. Even if you have a very high-end machine, you have 16 cores, right? If you have 16 cores and 100 processes, there's no way you can run them all at the same time, right? So some things are going to, 80 processes are going to be waiting at any given time because it has to do this juggling act. Right. Yep. Okay, so we don't know how to do any of this stuff yet, right? So we won't even get into how to create a process, even though you've been doing it this whole time and you haven't really realized it. Okay, so question?
I had a question. Since you said that waiting is when it's juggling between processes, it's only when it's working concurrently between two processes, are we in the waiting state, or during parallel processes as well?
So it'll be in the waiting or ready state just when it's not scheduled. So it could be running concurrently, it could be running in parallel. It just depends on the architecture of your machine, like how many cores you have. Right, yeah.
Is the OS running on the process as well?
So the kernel manages the processes. So you can think of it as a long-running process, but it doesn't really account for itself.
Right.
So it's always running, and it has a bit more things because it could interrupt itself and then wake itself up and just steal resources from everything, right? Because you're the kernel, you have to do the scheduling, so you have to be able to steal the CPU away. So, but you can think of the kernel, if you want to, as a long-running process, but it won't show itself in the list. Yep.
So the way the kernel would turn itself back on would be through some hardware trigger, right?
Yep. Yeah, because the kernel can access kernel mode, right? And it can access stuff that normal programs cannot. And one of the things is to wake itself up and steal the CPU back away from other processes. All right, so yeah, the scheduler is deciding that whole when to switch which process is running at any given time, right? So when you create a process, when we learn how to do that, we just kind of know the operating system has to at least load the whole program into memory before it can execute it, right? Remember when we had our ELF file, we loaded the entire file into memory, so that would have to be done before we can execute it, right? And while it's waiting, right, the scheduler, which again, coming later, decides when to transition it to running. And first we're going to focus on kind of the mechanics of switching processes because it's kind of important to understand any overhead that's going on and the mechanics of it. So if you're writing the kernel, which thankfully you don't have to do, this is kind of your core scheduling loop that will be in any kernel you ever see. First, it will, when decides when to switch. It will pause the currently running process. Again, deciding that process is the job for the scheduler, which we'll get into later. But the mechanics of actually switching the process is it will pause what's ever running, right? So it will stop whatever program counter where it's at. It will save the state, so it will save at least the program counter, so you can restore it later. So it'll save it to some variable, it'll save it into memory, so then it can start another process. So after it saves the information of the currently running process that we want to move to the waiting state, it will find the next process that it wants to run, right? Again, that's what your scheduler is going to do. It's deciding what to stop running and what to start running. So after it decides that, it will load the next process's state, which again would at least read the old program counter wherever it stopped at before, move it into the, replace the current program counter with that process's program counter, and then it would resume. So it would just pick up exactly where it left off. So this mechanic of switching between two processes is called a context switch, and we'll see it again. So one of the cruxes of this is we've been talking about the CPU being smart and taking away time from like interrupting the process and then taking the CPU away from that. So I've been saying that over and over again because that makes the most sense, and that's what's done, now in current kernels. But the alternative before, which you can guess was probably a disaster, is you can let processes, decide for themselves. So that's something called cooperative multitasking, where the kernel will not take the CPU away from any task, and it's up to the user processes themselves to say, hey, I'm done now. You can take the CPU away from me. It's fine, right? So you have to actually make a system call to inform the operating system you can take the CPU away from it. Yep.
Sorry, on the previous slide. So is this, like, we're talking about the kernel here, which is different than the operating system? Because you keep mentioning that, like, we don't have to worry about the kernel, but the kernel is doing this, right?
Yeah, sorry. When I say kernel and operating system, I kind of use them interchangeably. So a kernel is 100% part of the operating system. And other than that, operating system, it kind of gets fuzzy past that. But no matter what you say, for any definition from anyone on the planet, a kernel is part of the operating system. So throughout this, I kind of just say them interchangeably. So sorry. Yeah?
Does the kernel use a significant amount of CPU? Like, why do they do the other thing that the CPU is not used by the kernel?
Yeah, so we'll get into that because that's one of the kind of design decisions because, right, if the kernel is using the CPU, your user applications that you probably care more about aren't using the CPU, right? So that'll be one of the design decisions. So that's an important thing. Okay. Yeah, so again, cooperative multitasking, right? You'd have to make a system call to give up the CPU. Obvious disadvantage of this is if you don't make that system call, you get to run your program until you're done, right? So what incentive do you have to relinquish the CPU? And then one program can kind of monopolize the CPU and you can't really do anything about it. So that's like one really weird style of operating system. Style of kernel. Most kernels are true multitasking kernels where the operating system or the kernel itself will retain control and then pauses processes without you having any say about it. So if you do true multitasking, you could either, give processes a set time slot. So you could say you execute for 1 millisecond, and then you can kind of go through them round robin, which is a scheduling algorithm. And then you get 1 millisecond, you get 1 millisecond, and then just do that forever. You could also wake up periodically using interrupts, so you could have dynamic time slices for each application, and then set yourself an interrupt on the CPU to wake yourself back up and steal the CPU away from them. So, yeah.
Can a process still end itself early?
Yeah, so we did that before, so how a process ends itself is through that exit call.
I mean, give control away earlier.
Oh, give control away? So you can, but it's optional.
Right. In true multitasking, you
Yeah, yeah, you can. Most will have a way that you can say, hey, I'm good for now, right? I don't, versus what user programs takes. Well, so the important part of that is the mechanics of swapping these processes. So this is called a context switch. You want to minimize this as much as possible because that's pure overhead, right? Any time I take to switch between processes is time taken away from the user processes that you care about actually running, right? So at minimum, you at least have to save all the register state, which, you know, that's only a few bytes. That's not too bad. But even if you do that and you have to save all the values, it's kind of hard. So can you imagine if you didn't have any hardware support, you suddenly get access to the CPU, and then you have to save all the registers in their current state without touching any registers? Can anyone imagine actually doing that? Because it is impossible without hardware support, right? It's like saving something that you're trying to use to save it. It's just weird. So you need at least some hardware support for saving state, to save some registers that you're about to clobber to use to save the other registers, which is kind of weird. And you also might not care about certain registers. So if you don't have to save a register, you can save valuable, you know, nanoseconds by not having to save them. So some operating systems or kernels will go to great lengths to not save anything that isn't absolutely critical for restoring a running process. So, and context switching, again, is just pure overhead. It's the time you take to switch between two processes. You want it to be as fast as possible. And given that, you don't want to switch too fast. So say it took me, you know, 1 nanosecond to context switch. If my time slice is also 1 nanosecond, suddenly I'm wasting 50% of my CPU just switching between processes instead of doing anything. So there's going to be some trade-off here. And again, you can think of the flip side of that. If, hey, my context switch isn't that slow, and I just context switch, you know, every, say, like 5 seconds, well, you won't have very much overhead, but again, the responsiveness is going to suck. So you touch your mouse, and then maybe there's a lot of other processes, and you don't see the mouse updates till like 30 seconds later. Well, the extreme end of that is going to also be horrible, right? So you kind of want to minimize it as much as possible while also being responsive. So it's one of those things that's a fun engineering trade-off. Yep.
So why did you say that has to be hardware support for saving state? I mean, other than performance, is there any other reason that there needs to be hardware support for saving state?
Yeah, because the CPU is going to have to use some registers, right?
Oh, yeah.
Yeah, yeah. So at the very least, you'd probably need help, because if you were running code, you'd immediately clobber at least the program counter unless you recalculated it back by knowing how many steps. Then you'd probably be using some other registers that you'd have to be able to recalculate back, and it saves your life if you can just have a hardware instruction that saves like some registers to a memory location. Yeah.
So essentially, the OS, in trying to execute code that will save the registers, is clobbering the registers it's trying to save.
Yeah. Okay. Yeah, which is a fun problem where if you don't have any hardware support, you'll be sitting there for a long time. Yeah.
Does that mean that the kernel doesn't even really know it's saving the state because it's just hardware does it for it, or?
Well, so it would, you know, the kernel developers would read the documentation, know what it saves, right?
Right, but it doesn't have any like software that would tell it how to do that. So you just have hardware supposed to do it?
Yeah, so they'd start off with the hardware instruction and then have software that is a bit smarter that might like conditionally save stuff. So yeah, that's typically what's done. So they'll do hardware instruction for bare minimum and then try and do some smart software stuff to kind of ignore things it knows it can ignore. But that's like a way advanced topic that we won't have to get into. All you need to know is context switching takes time and it's overhead. All right, so let's talk about, I guess, the meat of this course and making system calls, because remember, we're kind of going to be living on this user space, kernel space boundary, and you do that through system calls. But right, so far we've never made a system call, and actually making system calls are rare. I'll save you looking at the documentation of system calls, but they're kind of a mess. So luckily, in kind of the Unix-y version of the C standard library, they clean it up a little bit. So most of the system calls have a direct C equivalent that kind of have a signature that you would expect, but they do some other things. So they set this kind of, you can think of it as a global variable called error number if anything bad happens to it, which will tell you, right, you'll be able to read a number, look it up in a table and see what the error actually is. It might do some fancy stuff where it will buffer reads and writes, so it's not making, you know, tons of small system calls, which waste a lot of time. It might try and simplify some interfaces, so like combining two system calls, for example, or it might add some new features on top of it just to make your life a bit easy. So we'll see kind of how to use them, but first let's even look at the exit system call because we used exit group. In C, we've just been returning from main, but your other option is to use exit, and this is just to kind of demonstrate additional features that C might put in. So if we write this C program here that just runs main, you can use this function called @exit to register functions to run when your program exits. So, right, the first line of main is I call @exit and register a function called fini, which is this function here, which will just put a string to the terminal that just says it's executing, right? And then after I register a function, I execute do main, and then I return. So anyone want to hazard a guess of what happens when I actually execute this program? What gets printed? So does do main get printed? Yeah, okay, most people at least think do main gets printed. Someone that thinks it doesn't get printed, want to tell me why? Anyone brave enough? Or everyone thinks it gets executed? Okay, well, let's just go ahead and execute it. Why bother guessing? So here's that same thing again. So I will make it. It's called @exit example. So again, this is in the example repository. So if I do that, both things get printed, even though that do fini is not in the main, right? I register it to happen when the program exits, and C has some niceties that, you know, lets you execute stuff at exit. So everyone get this? Yep. Why does do main get? Yeah, so this just registers it to execute when the program exits. So our program exits when it kind of hits this return statement, right? Because eventually this return will get fed into an exit system call. So this is kind of where our main exits, right? Yeah, return 0. So we can even make it explicit if you want. So I could just call exit myself there, right? So if I do that, if I'm not lying to you, then it should do the exact same thing, right? It should register this function, print the main, and then if that runs when it exits, you know, before this is done, it should print this, right?
So the @exit is basically saying that @exit you want to never shut a function?
Yeah. So this is just registering this. So whenever the program exits, I don't care how it exits, it will execute this function before it's done.
Okay, that makes sense.
Yeah.
Is it only when you exit main, or if you put @exit within a function, would it exit when that function exits? Or sorry, would it activate when that function exits?
So like if I just did, I don't know, something like this,
Yeah, you put it in there.
and then do that.
Yeah.
Okay, well here, I'll make it original again. So if I do that, it should do the same thing because it just registers the function. So it does the same thing.
Okay, so it's only at the exit of main that it calls.
Yeah, whenever exit gets called. So it doesn't even have to exit main. So here, if I'm not lying to you, it doesn't really matter, right? So let's say exit 1, and we'll put a 1 there so we can see that, you know, it's different than main returning 0. So say we'll do this, right? So if bar calls exit 1, then, you know, it should exit there. I should never see a return 0. I should never see a 0 exit code. And if I call exit, it should also run that do fini because it was registered. By default, you know, if you return from main, it will call exit because C is nice for you. But you could also call exit yourself explicitly if you wanted to. Yeah.
The difference between exit and return?
Yeah, so exit, so there's no difference between exit and return in the main function. Otherwise there is, right? If I just put a return here, it just returns from bar. Right? But exit and returning from main are pretty much the same thing. Yep.
You can only put one function here, right? Like, is in the stack if you stack the.
So if I register it,
Either a different function.
let's be clever. So like that. So you can do that. Right. So you can do that. So
So it's in the stack.
yeah, so it's actually defined. If you look at the C documentation for add exit, it will register them and run them in the reverse order that you register them in.
And does it run it like after or slightly before exit? Like,
So it runs like the first thing that happens after you call exit.
right. So before any of the exit code get executed.
Yeah, but because the last thing exit do will call the system call exit, right, which is kills it. Question?
Yeah, so like exit within your program is different than the exit group command because that's the actual system call, right?
Yeah, so exit is a C nicety where it adds features. One of the features it adds is at exit. So, right?
Okay.
Yeah, so that's a good question. So what I could do, so I could read the man pages, right? If I read the man pages of exit group, it says, hey, this is how to make an actual system call and not the kind of nice C thing. So if I make the system call, so let's go ahead and copy pasta. Oops, that's the calendar. Stop. If I include syscall.h and say, even I register the functions here, right? So if I run this, it would do, do main and then print the fini ones. But if I go ahead and do a system call, right? Syscall, this is how you do the system call, which is exactly what we saw in kind of the first lecture. Exit group status, let's call it 2. So this system call is not a C wrapper. So I expect now if I hit that system call, any functions I register, they don't execute, right? Because that's a system call, it's dead. So if I go ahead and compile this, whatever, it's implicit. So it just says do main because it's not using the C wrapper, it's dead as soon as it hits exit group. And you can see I definitely hit it because I don't return 2 from main or exit. I only do it as part of the system call and I get a 2 returned here. So yeah, this is kind of, if you use the C wrappers, some might behave a bit differently, again, to add additional features. So that's an example of one feature. All right. So the fun one, so kind of the first thing that we saw when we executed that really small hello world was an exec VE that I said it is now later. So what this exec VE does is it replaces the current running process with another program completely and resets it with whatever is defined in that executable. So it has the following API. It takes a path name So that's the full path of the program to load, which we now know if it's Linux, it's going to be an ELF file of some sort. And then it takes something we've all been familiar with in C. It takes argv, which is like actually countable is not going to count for you. It just wants you to put a null at the very end. And then there's an environment pointer where you can set environment variables. For now, we don't care about them. And then if it returns, an error has occurred, and it hasn't loaded a new program and started executing it. And if it's successful, it doesn't return because it just transformed this process into another one, right? So let's go ahead and see what that looks like. So here is our new main. So first, I'm going to print off, I'm going to become another process, and I will set up an array of character pointers. So the first one I will call ls, and these are the argv that you actually intercept when you have your main in C, right? So I'm setting them. So the first one I add is ls, which you might think is kind of weird. And then the second one is null, so I'm done with any arguments to the program. And then I just leave my environment as none. And then when I actually execute or do the execve call, I have to give the full path to the binary. So like if you type which ls, okay, it's an alias, but if it wasn't an alias, it would tell you exactly where that program lives. It lives in user bin ls, and then I give it the two arguments. So my array of strings and my array of strings representing the environment. So if I run this, anyone want to hazard a guess of what happens? Anyone brave enough to volunteer? Yeah.
I mean, it should just run ls, right? I'm going to become another process, and then ls the directory of whatever it is.
Yeah, so if I run that, right, it will print off, I'm going to become another process, and then execute the exact same thing as if you run ls with some caveats. Because if I execute ls, it actually looks like this, and it has colors. So it's actually a little bit different, and we'll see why that is. But you can see that as soon as this got executed, right, none of this code worked because I have another print statement that said if execve work, this will never print. Because if execve is successful, the process is just completely replaced, right? And then it just starts executing ls. So let's see, and we can see that I don't think I made a program called ECE 344. So if I do that and compile it, I should actually see some type of error code that says execve failed, right? So if I run that, it says I'm going to become another process, and then it gets into this. So execve, if you read the documentation, just says if it returns -1, it means an error has occurred, and it will print error no, or it will actually set error no. So I just save error no, and then this p-error functions will print off a error string that relates to that error no. But funnily enough, that in printing it, it might also encounter a different error. So that's why I save it and return it at the end, because if that p-error returns an error, it would kind of overwrite that error code. So that's why I save error number. And then in this case, right, we get execve failed, no such file directory, and then it returned a 2, which there's like, if you look at the error no error codes, 2 means no such file or directory, right? All right, any questions about that? Sure, over the.
So the error code that you have, the error message that you have on your terminal,
Yep.
is that from what you typed in, or is it because it looked up the error message from the error number?
Yeah, so this p-error code will put the message you put here, like here, and then just fill in the rest of it from the error no that got set. So you don't have to look it up yourself. Sure.
So I noticed you passed ls as like as the first argument of argv. That's just kind of like convention, right? That you see it at the front of argv. You don't actually have to do that, do you?
Yeah, so that's a good question that I kind of repeated myself. I'm using ls, and then the first argument is ls, and that's right. By convention, the first argument is always the name of the program that was used to execute it, because if I go ahead and change it to haha or something like that, right? If it doesn't actually, who here has ever read argument 0 and then done anything about it? Probably no one, right? We all ignore it. So in that case, we get the same output because it doesn't really matter. In some cases, it could matter. So some people are very, very clever. So something called BusyBox, which implements like CP, RM, and all of that, is actually one binary that will change how it behaves based off this first argument and based off how you call it. So you can do that. You will probably never do that, though. So it's pretty much by convention. It should be the same name as the executable, but generally it's never used. Yep.
How does ls know which directory to print if you don't pass in any environment variables?
So the kernel is smart and knows where it got executed from. Yeah.
What exactly is the role for the environment variables?
So the role of the environment variables is people generally just set them to and then read them while the program's executing to change its behavior. But it's just I guess a kernel-supported way of passing variables around without having to set them through a command line. Yep.
Can you give me an example of how the environmental variable would be?
How you would set them, you could just do, I don't know, just something like that. Like how you would set them?
No, like I mean, like how would what could I use the environment variable for?
Oh, so in your program, you can use, it's called getEnd, something like that. And you can read an environment variable from there and get its value, and then change your program behavior based off that.
So like whatever program changes that I use, it would be with respect to that environmental variable?
Yeah, so you can say, you know, some programs say you can set some settings by command line, or you can set them by setting a special environment variable called whatever. So it's just different ways of passing variables. So like you can see your current, so if I type env, it shows all the current environment variables set that might be used by different programs. Is there anything that's good? So like for example, one of the ones that's commonly sent is the user. So by default, if you run your program, it will just pass all the environment variables. So most programs by convention will be able to access user and then know what user executed it without having to pass anything on the command line. Yeah.
So what is like the actual purpose of exec RFB? Like what does it do? What is the like exec DE do?
So it replaces a currently running process by loading that program and then starting executing that program.
But like doesn't it know already from like the path name what program it needs to like the file path?
You mean this one? Like this variable?
Yeah, doesn't it like already know which program is supposed to be executing the path?
No, because so like I'm typing into bash right now or ZHC, and it has to make that system call. So it has to know what you typed and it passes it. Right. Yeah.
Quick question. So if you remove the ls after the bin, and you just keep the ls that is there in exec the arg
Like this?
no, just remove the ls from that and just keep the ls with it.
This?
Yes.
So that is not permission denied because that's actually a folder. All right, give me 1 second. I'll wrap this up and we continue on Discord or something. So it's that. So yeah, your operating system has to load a program, create a process with that context, maintain process control blocks, switch between running processes using a context switch, and replace programs using exec VE. All right, boom for you. We're all in this together. All right, out of time.